Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, so this is lesson 6 or 5.2.6, which is the last lesson that we are going to do before we take the first chapter 5 test. This is a two-parter, and each of the smaller parts is actually not the longest lesson ever, which is kind of nice, but if I tried to do them all in one day, it would be very tedious and long. So we're going to break it up into two parts. Each part should be between 15 and 20 minutes long, so let's get started with part number 1. In lesson 5.2.5, you use systematic lists, probability tables, and probability trees to organize the outcomes of different probability situations. Today, you're going to use, or we will use, a probability table to organize events when one outcome is more likely than another. So there's going to be a little twist on the probability table kind of a situation. Let me actually put a screen here first. Let me change it to a color that I like for aesthetics. Okay. Nina's buying a new pet fish. At the pet store, the fish tank has an equal number of two kinds of fish. So you got tetras or guppies that she could purchase. And each kind of fish comes in 4 different colors. So you got your yellows, your orange, your blue, and your silver. So I've highlighted the type of fish in yellow, because that is one of our events. The other color is blue, and that is for the second event, which is obviously the color. So there are an equal number of each color of fish in the tank. We say that because it's kind of an important idea for this probability to work. We know that that is not actually the case. If you go to any pet store and you look in the fish tanks, there's no way you've got equal numbers of each type of fish and each type of color in there. But for the purposes of probability in this lesson, we're going to pretend like that's possible, and that's the case. So if Nina scoops out a fish at random, what is the probability that she will scoop out a silver tetra? So taking a look over here, you can see all the different possible combinations, right? You could have a tetra that's yellow, and maybe I'm going to do the color first, an orange tetra, a blue tetra, or a silver tetra. And then you could have a yellow guppy, an orange guppy, a blue guppy, or a silver guppy. So of all those possible combinations, what's the probability that she would get a silver tetra? And so what I would do is I would look, here's the silver, here's the tetra. So that is 1 out of the 8 possible combinations. So we would say the probability of getting a silver tetra would be a 1/8 probability. Now, Nina has set up a table below to organize the different possible outcomes. She represented the kind of fish on one side of her table and the color of the fish on the other. So here's the colors across the top. Here's the kind of fish on the side. Notice these fractions here? What do those fractions inside her table represent? Notice that this combination means that there's a 1/8 probability of getting a yellow tetra. There's a 1/8 probability of getting an orange tetra, and so on and so forth. So if you were thinking that those fractions all represent the probabilities of getting each of those individual fish combinations, then you are correct. All right, so as Nina looked at her work, she noticed her table looked a lot like a rectangle with the area parts divided. All right, the area divided into parts. Help me calculate the probabilities, she wondered. She used the length and width of the silver tetra section to set up this equation. 1/4 times 1/2 equals 1/8. How does the equation relate to length, width, and area of this section of the rectangle? Does this match the probability from part A? And so the answer is yes, it does match the probability, right? 1/8 we have here for the silver tetra is the same as the probability that we had gotten from using the probability tree. But what's going on with that 1/4 and that 1/2? Well, the 1/4 and the 1/2 are kind of like the length and the width, or the width and the length of a rectangle. And to find the area of the rectangle, you would multiply them together, right? So let's think about this for a second. What is going on here? If you just wanted to find the probability of just picking out a tetra and you did not pay any attention to the colors, wouldn't you agree that the probability of getting a tetra would be equal to 1/2, since there are two different kinds of fish and one of them is the tetra? And then if you were going to think about the probability of getting a silverfish, if you did not pay any attention to the kinds of fish but only focused on the colors, there are 4 different colors and one of them is silver. So what we have here is a situation where we're taking the color and taking the kind of fish and we multiply them together, and that gives us the probability. And we sort of were getting to that in our last lesson. If you recall, let me go ahead and throw this in here for a second. In our last lesson, when we were talking about how we had 2 types of flavoring of ice cream. You had 3 different types of mix-ins, and you had 4 types of fruit swirls. And since this is compound probability involving the word and, it's going to be one of these and one of those and one of these, you would have a total of 24 different combinations or outcomes for that particular situation. So this is compound probability involving the word and, which means there's going to be some multiplication. So how many different choices were here times the number of choices here times the number of choices here is going to give you the total number of possible combinations for this situation. How many different choices were there for fish? There were 2 different choices for fish. How many color combinations were there? 4, or color choices. So that means that there will be a total of 8 different combinations. And each one of these choices represents 1 out of the 8. So there is absolutely a multiplication process that works here. So what is the area of a complete large rectangle in this situation? Well, the complete area of everything is going to be a total sum of all of the different parts. So 1/8 plus 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 1/8. When you add up all those probabilities of all the different fish combinations, you get 8/8, which is equal to 1, which represents 100% of all the fish that are in the tank. So using this understanding of multiplication to find probabilities when you've got compound probabilities might help us when we're creating probability tables for more challenging situations. So let's take a look at a more challenging situation, testing the area model. Nina decided to see if thinking about finding area would help her find other probabilities. She put 3 cubes into a bag. 2 of them were blue and 1 of them was yellow. She pulled out 1 cube and put it back in the bag. Then she drew another. So use a systematic list or a probability tree to organize the possible color combinations she could get. So remember, you've got 2 different events here. You're pulling out a cube 1 time, and then you're pulling it out again. So this is the first time she pulled it out. This is the second time that she pulled it out. So then she drew another. So I coordinated those 2. And notice that there are 2 blues and there's 1 yellow. So if you were to make a list of all the possible outcomes here, the list of possible outcomes would look like this. You could get a blue blue, a blue blue, and a blue yellow, right? But then you could also do that again because you've got 2 possibilities of blues on the first pull and 2 possibilities of blues on the second pull. So you could get a blue blue again, a blue again, and a blue yellow again. And then the third set of possibilities would be a yellow, then a blue, a yellow, then a blue, or a yellow and a yellow. So we've got a total of 9 different possible outcomes or combinations for pulling these cubes randomly out of the bag. And this is the list of all of those outcomes. So it says use a list to find every possible combination. How many are there? And what is the probability of getting blue blue? So let's go ahead and highlight all the ones that are blue blue. Here's a blue blue. There's a blue blue. There's a blue blue. There's a blue blue. That's a total of 4 possible combinations out of the 9. And so that means that you would have a 4/9 probability or 44.4% chance of reaching in 2 times in a row and getting a blue cube each time. So this time Nita decided to create a table at the right. And I want you to see how this table sort of matches this list of outcomes that I generated from looking at my probability tree. Notice how, once again, you've got 2 different events. The event that I've highlighted in green means that the first time she pulls, she could either get this blue one, the other blue one, or the yellow cube. And then the second time she draws from the bag, she could get that first blue one, the second blue one, or the yellow that happens to be in there. So when you set up this probability table this way, you get pretty much the identical result as what we got here when I listed all the different outcomes. Is the probability the same here? Do we still have 4 out of 9? And the answer is yes, we do. So now let's take a look at this. This is a more condensed and efficient way of creating the probability table, where we create the rectangular table, but instead of accounting for every single possible outcome of pulling out the first time and pulling out the second time, we are going to write the probability of the first time that you pull out. Wait, which one was the first one? The first one was the green, right? Okay. So the first time you pull out, you had a 2/3 probability of getting a blue that first time, and you had a 1/3 probability of getting a yellow that first time you pull the cube out of the bag. Then the second time you pull the cube out of the bag, you had 2/3 probability of getting a blue and a 1/3 probability of getting a yellow. So if we're going to try and find what is the probability of getting a blue and getting another blue, should I have used the word and instead of the little symbol? I probably should have. Let me go ahead. I don't like that thicker marker. We'll do that. And another blue means we're going to multiply these probabilities together. And so the probability of getting a blue in the first place was 2/3. The probability of getting a blue in the second place was 2/3. So 2/3 times 2/3 ends up being 4/9, which is our probability here. So that's what we're going to show here. We're going to show how the probability of getting a blue is really the product of multiplying 2/3 to 2/3. The probability of getting a blue yellow is the product of multiplying 2/3 times 1/3. The probability of getting a yellow first and then a blue would be the product of those two probabilities, and then the probability of getting a yellow and then a yellow again would be the product of 1/3 and 1/3. So what is the area of the section represented by blue, blue? Well, this area would be 4/9, right? Does this match the probability that we found in all the other situations? Absolutely. Every single time we do this, regardless of whether we use the condensed multiplication probability table, whether we use the expanded out probability table, or whether we choose to use a probability tree, we always get the same results. So if we can be as efficient as possible with our data to get our answer, then it seems like that would be the way to go, right? Seems like it. How much time do we have? Oh, we're doing great with our time. All right, I promised you today's lesson was going to be a little bit shorter. So what I'd like for you to do is go ahead and do today's homework. I believe that was problems 83 through 87. Is that what it said for part 1? Yeah, 83 through 87. Tomorrow we will complete, or the next video, I should say, will complete this lesson, and then there will be another set of problems. I think 88 to 92 might have been those problems for part 2, even though I didn't list it here. So yeah, let's go ahead and wrap this up right now, and then we will do the second video later. Take care. Bye.
Hey, feeling good.